There we go.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we've got a really interesting hangout planned for you today. We have Dr. Mark Clampin from the Goddard Space Flight Center here to talk to us about exoplanet observations, both past, present, and the future. And so we're looking. This should be a very interesting hangout. So we hope you will bring lots of questions and comments. Which brings me to how you can interact with us. We hope you will send us questions with the Q&A app on YouTube and the Google Plus event page. We're also monitoring the Hubble Hangout hashtag on Twitter, and you can also comment on the Google Plus event page itself. So we're monitoring all these different avenues for you to interact. So we hope to get lots of great questions from you later in the Hangout. With me also is Dr. Carol Christian. She is from the Space Telescope Science Institute as well. Hi, Carol.
Hello.
And Scott Lewis.
How's it going, Tony?
Hey, you ready to drive the internet?
I'm always ready to drive the internet.
I know, you're an expert driver, NASCAR of the internet drivers.
F1, no NASCAR. I know how to maneuver.
Picky.
So as I mentioned, our guest today is Dr. Mark Clampin. He is the Observatory Project Scientist for the James Webb Space Telescope at Goddard. Welcome, Mark.
Hi. Thanks for having me.
I'm really excited to get you on in a hangout because you've got a lot of great research going on. You're involved in all kinds of great things. But first, I have to ask you, Observatory Project Scientist. How is that different? What does that mean? And how does that differ from, say, just a regular project scientist?
Well, it comes down to the fact that James Webb Space Telescope is such a massive project, and it's a very large telescope. So my job is to be responsible for the observatory, which is three pieces: the telescope, the sun shield, and then the spacecraft bus. So my job is to work with the engineers to make sure that the science requirements for the telescope for the observatory are met or preferably exceeded. And when they have problems, I'm the guy that gets to sit down with them and help them figure out how they can meet our requirements and still, meet the budget or the schedule.
Oh, so really not very much then. You don't really have much to do with
yeah, he's never busy.
No, they keep me very busy. So
you sound like an underachiever there.
Yeah, really. Is that all you're doing?
Step it up a bit.
Is that all? Yeah, really. Yeah. Jeez.
Okay, well that sounds great. We hope to get some more insights into the status of JWST a little bit later on in the Hangout. But before we do that, I want to talk a little bit about your research interests. Before you were building the James Webb or coordinating all these efforts, what's your primary research interest?
So my primary research interest has always been direct imaging, or taking pictures of debris disks, which are the early stages of the formation of planets, and then actually trying to directly image planets themselves. So I started off 20 years ago building an instrument called a coronagraph, and I guess we'll get into how coronagraphs work later on, for telescopes that would be put on the Chilean telescopes down in at La Silla and then La Serena. And then I slowly evolved to working on flight hardware, and I actually helped build the advanced camera for surveys, which had a coronagraph.
That's on Hubble.
That's on Hubble. So I've always kind of worked on building hardware to do this kind of problem, and we started off, as I said, studying debris disks, and the more you get into imaging debris disks, the more you want to sort of go the next step and actually be able to directly image the planets. So that's what I've been kind of working on with Hubble on and off for the last 10, 15 years.
Right. So today's Hangout topic obviously is about exoplanets, but one of the things that really amazes me about this branch of astronomy or research is that this really is a pretty brand new research area, isn't it? You said yourself 20 years ago. That pretty much marks the beginning of exoplanet research, doesn't it? I mean, we haven't been doing this for very long.
No, that's correct. It's about 20 years, and it's just a rapidly expanding field. A lot of the new young people coming into astronomy are all sort of coming into this field because there's just so much going on. There's new planets being discovered every day. It's just a really exciting and dynamic field right now.
And correct me if I'm wrong, but this field, exoplanet research, really had, I think, pretty humble beginnings, from my understanding. I mean, I remember at the High Altitude Observatory, it was people there observing a project called STARE, S-T-A-R-E, which basically used Meade telescopes in a parking lot to, and this was with Dr. Charbonneau and was it Mike Brown? It was, oh gosh, I'm dating myself now. But anyway, they were looking at exoplanets, or trying to find exoplanets, presumably with the transit method, which we'll get to in a minute, with amateur-grade instruments.
Exactly. I mean, this. Well, as you said, we'll talk about transiting exoplanets in a minute. But I think one of the amazing things about studying transits is you can actually stand in a car park like Dave Charbonneau did with a celestron telescope and take data that shows you there's an exoplanet orbiting a star. That's pretty amazing.
Yeah, gosh, it was about a year and a half ago. I held a hangout on here where I had one of our amateur astronomers that works with CVSO, and we did a live observation of a transiting exoplanet. So we're able to get the data there and show the curve going on afterwards and talk about what was going on. These are things that can be done by everyone, and it's amazing. And this is how we are using advanced telescopes, out orbiting in space, and also very large telescopes here on Earth to discover completely new worlds.
Exactly. The transiting exoplanet method is great because it just scales from your telescope in the car park all the way up to James Webb Space Telescope, and at every step or every scale you can make lots of really amazing new discoveries.
All right. Well, let's go ahead and bring that up. So, Scott, I believe you've got a good illustration of what the transit method is. So let's talk about, before we get to the future of exoplanet observations, let's talk about how it's been done in the past. As we've talked about, exoplanet research is a new field, very young, very exciting, red hot right now in astronomy, and the observations have been done primarily by looking at very, very tiny dips in brightness of a star, and Scott has this up now. Basically, when a planet passes in front of a star, it gets just a little tiny bit dimmer, and as the light is blocked from the star. And Dave, I'm sorry, Mark, I'll let you go ahead and explain this animation a little bit.
Okay, so the animation is just showing what happens when you look at a star where the planet is actually moving across the face of the star as it orbits that star. And so what happens is you see a very tiny dip in the amount of light coming from the star as the planet orbits across the face of the star. And the dip is basically a function of the area of the star that you're looking at and the area of the planet. So large gas giant planets like Jupiter's might produce a dip of a few %, whereas if you were looking at a terrestrial Earth-like planet, then the dip is much smaller. It's about 0.05%, and then it becomes a very challenging measurement. But just looking at some of these big Jupiter planets, that's the kind of stuff you can do with a very simple telescope, as we were talking about a few minutes ago.
Right, and this was among the first measurements we made, or the first ways in which we detected exoplanets. And this is an indirect method, meaning that we're not seeing the planet directly. We're seeing the effect of that planet in orbit around the star, and inferring the existence of that planet being there. How hard is this to make? I mean, we said we can do it with amateur-grade instruments, but we can do better jobs with bigger telescopes. Correct? I mean, how hard is this measurement? It's not too hard, as I said, if you're trying to just do gas giant planets where you're looking for a few % dip. As you start trying to look for terrestrial planets, then it becomes a real problem because you need to have extremely precise photometry, and that's why we've had to go into space to really look for the Earth-size planets, and that's, as you know, that's what the Kepler mission has been doing for the last 6 or 7 years. It's just been staring at 150,000 stars, trying to find the ones that have transits that are directly traceable to something the size of a sort of small rocky planet. So it gets very easy to very, very hard.
Here's an example for Kepler too, and you'll be able to see. I'll have it pop up here in a second, where we're seeing those dips in brightness that's being detected on the lower right-hand side of the screen. Right here.
Right.
So that,
Right.
that
And
big dip.
that's a very generous light curve.
Right.
Yeah, really
Right.
beautiful.
Yeah.
No noise.
Right, and when you look at real data, you know, without doing the analysis of the data and the processing, it's very hard, especially for the small planets, to see any dip at all. You need a
Right,
pretty
that's a good
big
point.
planet to give you a... So this technique really thrives on, especially when you're trying to do the small planets, on having as much light as possible, even from very bright stars. So this is one of the reasons why JWST is going to be such a powerful tool for doing this kind of science.
Yes, we'll get into that in a little more detail in a bit. But
And we have used HST to do this. I mean, people did want to try and just get a feel for an HST-sized telescope, what could be done. It's not a primary thing that we do because these other observatories will concentrate on that, but a few observations were taken with HST just to make sure we knew what we were up against.
Right.
Yeah, and I think, Carol, and correct me if I'm wrong, but the reason HST isn't ideally suited for this kind of work is that generally these light curves take many days to, sometimes, depending on the period of the planet, to create, right? So you really kind of need to take up a lot of Hubble time to get a decent curve, right?
Right, and that's why, as Mark says, the strategy that Kepler is using is so important. So you can take a long time to make sure, and you can't just have one sample. You can't just see a dip once and say, oh, there must be a planet. No, it has to be periodic. It has to keep coming back. It has to be similar every time.
Right.
And so you need that. And so Kepler, in staring for many years at the same region of the sky, can then do that. And as they acquire more and more data, they can, as Mark said, get to tinier and tinier planets that they can discover, because initially the data is a little noisy, so you have to keep accumulating the data until you get good statistics and you're confident about that you've detected a transit.
Right. Yeah, this is a great segue into the past of observations. So Kepler was designed. I'm just going to fill in the gaps of what we didn't say about Kepler. Is it's staring at one spot in the sky, looking at over 150,000 stars for a very, very long time. 5 years, I believe, was its mission. It went a little bit past that before it stopped being able to point precisely. So we got 5 years of Kepler data looking at the same 150 some odd thousand stars. And as Carol said, we built this up over time to get these tiny dips in brightness, and it uses the transit method. But that's not the only method to find these exoplanets. It's just what Kepler uses, and it was the beginning. It was the way we started finding exoplanets in the first place. But there's another method. It's called the radial velocity method, and Scott has an animation that sort of illustrates that. And Mark, can you give us some insight into what that method is, and what are the best ways of making that kind of measurement?
Okay, so the radial velocity method was actually the first one that made a exoplanet discovery.
Oh, that was first. I had it wrong, and my apologies. I said.
And it was Michel Maillard, Jeff Marcy, some of the early pioneers in this field. And the basic idea is that if you have a star on its own, and you add a planet, as the planet orbits the star, the combined center of gravity of the two is just slightly offset from the center of the star, and so you see the star, essentially orbit a very small amount, and thus it's coming towards you and going away from you, and you can actually measure that velocity in the dispersed light from the star. You need extremely high sensitivity to do that, because you're talking about measuring the order of kilometers a second differences in the lines as they move backwards and forwards. So to do that, you need very large ground-based telescopes that disperse the light, a very large amount. But a large number of the original planet discoveries were found using this technique, and then we realized that some of these stars were probably transiting, and we started to follow up the observations using the transit technique.
Right, so let's bring them together real quick. So each of these methods has their own strengths and weaknesses, and we can get different information about the exoplanet from each one. You want to tell us what can we learn from transit methods about exoplanets versus radial velocity?
Yeah, I think that the story really is that when you put the two together, if you combine a system where you've got radial velocity measurements, which give you the mass times m sin I, or with the inclination, and the transit method, which gives you some idea of the radius of the star. When you combine those together, you can actually back out the mass, the radius, and then you've got some idea of the density. And since you know the radius of the star, you can start making inferences about the composition of the planet. So when you put these two techniques together, you start to get really useful data, you know, the kind of stuff astronomers like, where you plot mass and radius on a chart, and you can start to categorize these different planets.
So Kepler does not do that, right? It just does the radial or the transit method, correct?
Right. So Kepler was designed to answer one very simple question: what fraction of stars have a terrestrial or rocky planet orbiting them? So it's really an exercise in statistics, but that's a very important number to know, because ultimately we would like to directly image Earth-like planets around other stars and even get spectra of them, but we can't really build a telescope to do that until we know what the probability that if we look at a given star is going to have a terrestrial planet. It really determines how big your mirror has to be. So that's a very important number that we need to understand, and that's what Kepler was designed to do.
So we got transit method will show you something about the radius of the planet, and the radial velocity method will give you some idea of how massive the planet is. So putting those together, we can get a pretty complete indirect picture of the exoplanet itself. But we're not satisfied with that either. I mean, this is how it's been done with the past, and now we want to look at these things directly. You said at the beginning that one of your research interests is to observe exoplanets directly. Can we do that now?
Yes, we can. So observing exoplanets directly is a real challenge, because they are extremely faint and they're orbiting very close to stars that are extremely bright in contrast. So this whole field we call high dynamic range imaging or high contrast imaging. And the basic idea is that you need to figure out a way whereby you can essentially suppress the light from the star you're looking at, so that you can increase the region of contrast around the star and be able to directly image a planet. And just to give you an example, if you were looking at our sun from another solar system, Jupiter will be about 1 billion times fainter than the star. And if you were looking at the Earth, it will be about 10 billion times fainter, but also much closer. And it's a very difficult, very challenging problem. You have to think about a lot of different optical aspects of your telescope design when you try to do this.
So I was just going to comment and jump in here, is that in the initial, in any of these studies, especially the transit method, initially they were large planets that were found for the reasons that Mark was talking about, is you need a big dip, but you needed to go around several times. Right. So you needed to do that. You can't have, it's hard to detect a planet that is going to take 10 years, you know, to cross in front of its star from your perspective. So what happened was that many of the Jupiter, Saturn type planets that were found were relatively close to their parent star, which is not the situation that we have in our solar system. So that was a puzzle for a while, but it's an artifact of the fact that that's how the transit observations work, is that they are predisposed to find things that block a lot of light and are close to the parent star and go around a lot.
That's right.
But that doesn't mean those are the only planets around other stars.
Yeah, there's an inherent bias in that observation, because you know it has to pass, the planet has to pass between us and the star to even know it's there. We don't get those other.
Right, and also Mark had mentioned inclination. So if you have an inclination which is close to what we call edge on, so the planet, when it does orbit, it crosses in front of the disk of the star, we can see that dip. But if our vantage point is different, we may not ever see that.
That's
so there
right.
are stars that have planets that we just haven't seen them, so we need these other techniques.
So if anything, Kepler has undercounted its region of the sky that it's looking at, because it's only counting those with the line of sight issues that we just talked about. Scott, can you put that that one animation back up where the planet going around the star? And while
I
he's
had a
doing
bunch.
that,
They were all.
They all did that.
the one you showed,
One.
the first one you showed.
First one, yes.
We're talking about the transit method and the planet going around. Which one? All right.
Which one? Am I?
The show is on exoplanets. Can you show the one about
that one with the
space?
star in it?
Yeah,
No,
the
show
one
that.
about
Yeah,
space and astronomy.
Yeah,
There you go.
we showed that
There
one.
we go.
Yeah.
Show that one with the star in it. Yeah, that one. Okay. You got to read my mind, Scott. I thought that's what you did. So,
I'm not
Mark, it
paid
sounds
enough
like
to read your mind.
to directly see this planet, we're going to need to block the light out from the star somehow. And to do that, we use something we use something called a coronagraph to see things close to the sun. To see, for example, the atmosphere of the sun, we block out the disk using just an occulter. Here, is it better to in order to see this exoplanet directly, the one that Scott is currently showing, we would have to somehow block the light from that star, and we would see it like stop it when it gets off to the limb of the star, like right there. If you can stop it somewhere when it gets to the side. There you go.
Yeah.
Well, that's close enough. So
Yeah.
in order to see that, we'd have to block the light out from that star, right?
That is correct, yes.
But we need the orientation to be such that it's either off to one side or the other. This is only for exoplanets that are within our line of sight.
Exactly.
So-
And so Scott's just put up a picture of a system called Fomalhaut, which is one I actually studied with the Hubble Space Telescope. And in this one, you can actually see how the coronagraph on the advanced camera and subsequently STIS worked. So we block out the light from the central star, in this case Fomalhaut, which is an extremely bright star in the southern hemisphere. And what you see in that image is a ring of dust, very analogous to the Kuiper Belt disk in our own solar system. And then just inside, it's highlighted in a box, several different observations of a planet that's actually orbiting Fomalhaut. And this we were able to do using direct imaging, high contrast imaging with the Hubble Space Telescope.
Yeah, and you said it yourself. The debris disk around that is very visible here.
Yeah.
So how is this done? How do you block out the light from these stars?
So put very simply, you have a some kind of mask in your optical system. So you focus the light from the image down onto a very small mask, and then you have to re-image that light and also block out a lot of the scattered light that's produced by optical effects in the system. Once you've done that, you can then re-image the picture again, and it gives you a pretty good what we call circumstellar image, an image of the region around the star. You don't always get to remove most the light from the central star, so certainly in the case of Hubble, which cannot achieve the kind of contrasts I mentioned. So Hubble, we can get contrasts of about 1,000 to 10,000 maybe. So to do Hubble observations, we actually take a picture of our system, and then we take a picture of a star that we don't think has a planet, or several stars that we don't think have a planet, and we actually have to do a subtraction of one from the other to remove the residual halo of light so that we can actually find these planets.
Oh, wow. Okay. So I understand in this diagram that's up right now, I understand the occulting spot part. I get what's going on there, but I don't understand the LEO stop. What is that doing?
So the LEO stop is to deal with what we call diffraction. So every edge in the optical system, the telescope spider that holds a secondary mirror, the edge of the secondary mirror, the edge of the primary mirror, is diffracting light, and you can, to first order, think of that as just scattering light. And so that light needs to be suppressed. So the LEO filter just removes all of that scattered light in what we call the pupil plane. And then when you re-image, you don't get all of that additional stray light or scattered light contaminating your image.
Okay.
Now this is a very simple coronagraph design. It's the original LEO design that I showed you. There are lots more now which are infinitely more complicated, that use bending mirrors, deformable mirrors, and there are also designs that use very small interferometers to interfere pieces of the light in the focal plane with each other to block out the light from the central star. So there's a whole universe of different approaches to doing coronagraphy now based on different optical techniques.
Right. So the future of exoplanet observations is to see them directly, and let's talk about what JWST is planning on doing. They have, correct me if I'm wrong, but is that what the microshutters are supposed to be for? There's these things called microshutters on JWST that are designed, I think, to block out light from stars. Is that correct?
The microshutters are actually to allow us to look at multiple objects at the same time. So they're more geared towards the deep imaging first galaxies problem. But several of the JWST instruments have coronagraphs built into them that will give us different levels of performance in the near-infrared and then the mid-infrared. So in the near-infrared, we use very traditional coronagraphs, much like the one we just saw in the figure. In the mid-infrared, at longer wavelengths, we actually use a small interferometer where we divide the focal plane into 4 and then interfere pieces against each other to block out or null the light from the central star. So JWST has some extremely capable coronagraphs, and they will allow us to really study that parameter space that isn't sort of met by doing transit observations to further out objects at orbits of, roughly akin to Jupiter and further out.
Okay, well, you brought up the topic I want to get to. As an exoplanet researcher, what most excites you about JWST? I mean, what kinds of planets are we going to be able to image with that?
So I think, for me, the two most exciting things are, one, being able to take images of systems like Fomalhaut at different wavelengths. I think we will really be able to sort of piece apart that system now. By imaging at different wavelengths, we can see different distributions or different populations of dust within the system, and we can also hunt for the other planets that we think might be there that we can't right now see. As far as the transiting systems goes, that's where I think JWST is going to be the killer application. It just has everything you need to do really fantastic transiting exoplanet science. And we haven't actually talked much about doing spectroscopy, but the next step in doing transiting observations is to disperse the light as you measure the transit. And by doing that, you can actually back out the spectrum or the dispersed light signature of the planet's atmosphere. And once you can do that, then you can start studying lots of different planets, looking at their atmospheres, and really doing a lot more comparison of different types of planets.
So can you quantify that a little bit? How? I mean, presumably we're doing. Are we able? Well, let me back up. Are we able to do this now with anything that currently exists? Get the composition of exoplanet atmospheres.
So we can do this now with HST. They're extremely hard observations, as you said, because a single transit can last many hours, and Hubble goes around the Earth every 90 minutes, so you only get half of 90 minutes to actually do science. So you have to piece together several transits. And Hubble doesn't work out into the full range of the near-infrared. It does 1 to 1.7 microns rather than 1 to 5, which JW can do. And then JW can also do the 5 to 30 range.
I like how you call it JW. It's kind of like you're on first name basis with it, just doing JW. Yeah.
It's like you and NDT, right, Tony?
That's right. I call Neil deGrasse Tyson NDT because we're like that. So yeah.
And the other thing is that Spitz has also started to do this, but Spitz has to build up the spectrum by taking images, and then you get a spectrum with what we call a spectral energy distribution, 4 or 5 data points, and you're trying to fit to those. So being able to get a real spectrum with a very high resolution in a single transit, which is what James Webb will give you, is going to be very powerful.
Okay, that brings to the question I initially wanted to ask you, which can you quantify a little bit how much better JWST might do than how these current observations are being done, or I don't know, maybe orders of magnitude estimate?
That's tough, but the bottom line is that most of the observations we're doing now, the resolutions may be the order of spectral resolution of 100. With JW, we can go to 2,000, 3,000 spectral resolution, and we can get a full transit in one visit for a lot of gas giant planets.
So you've said that the transit method is going to be one of the bread and butter applications of JWST, or you said JW.
Yeah.
Man.
What did the results from Kepler surprise you at all as a scientist? Just how many planets Kepler found?
I think one of the things, I guess no, I am actually one of the believers who was expecting that Kepler would find a lot of planets, and it has. I think it's been one of the surprising things is just how many small planets and also planets in the sort of super-Earth range midway between the size of our Earth and Uranus and Neptune. So it's discovered. For me, one of its big discoveries is just how many super Earths and small rocky Earths there are out there.
Yeah, I bring that up because one of the big things that I always hear JWST project members talk about is that one of the most exciting things about the James Webb Space Telescope isn't the kinds of science that we know we can do with, or the kinds of answers to questions we know we're going to get, but the answers to questions that we haven't even thought to ask yet. And so there's a whole unknown area of things that we expect JWST will show us. And I use Kepler as an example because from my mind, I think it's just blown everybody away. I mean, staring at one spot in the sky for years and years is a pretty simple thing to do, and it blew us away with what it taught us about our place in the universe. So I'm just excited about JWST coming up, but that's not all. Let's talk about some other things.
Well, real quick before we do that, for those that aren't aware of just how spectacular JWST is, I mean, I know you and I have done some outreach with the full-scale model, but here's a wonderful animation just showing how fantastic JWST is. So it's going to be out at the L2 point, and it is the area of a tennis court and 4 stories tall. Is that about accurate?
That's right. It's the largest tennis court in orbit.
And as I was telling you earlier, Tony, I just participated in the first ever deployment of those 5 layers on the ground, and it's really amazing when you're standing inside the tennis court.
I know, and I want to get you back in another hangout to talk about that specifically, because I want to know how it went, if everything's on track, if you guys learned anything new doing that deployment. But unfortunately, we don't have time because I want to get to so many other things. So mark your calendar and for another hangout where we'll go into this. Okay, so what's the next? I'll let you drive this part of the conversation.
Yeah.
What do you want to talk about next? We've got all these different missions coming up. We've got something called At Last. We've got TESS. We've got Star Shades coming up. Pick one.
So let me start with TESS. So as you said, Kepler has done a great job of answering the question, what's the probability if I look at a star, it's got a planet, a terrestrial planet around it. But a lot of the targets that Kepler's identifying for us are just way too faint to be able to do good spectroscopy with James Webb. So it turns out that even though James Webb is 6.5 meters across, the kind of signal strengths you need in order to be able to back out the spectrum of these planets, you need much brighter parent stars to be able to do the observations. So my colleague George Ricker at MIT came up with a mission which I'm participating called TESS. And the basic idea of TESS is we're going to go find nearby transiting exoplanetary systems around bright stars that people can study using JWST or even the next generation of very large ground-based telescopes. So that raises a problem. How, you've heard you have to stare for a long time. So if you wanted to map all the bright stars in the sky, how do you do that? And George came up with this very neat approach using TESS, where we will map out the whole sky over 2 years and basically study most of the bright stars to see which ones would make great candidates for follow-up with JWST.
And again, that's a transit telescope, right? It's looking at transits.
Exactly. It's a transit telescope. It has 4 cameras, and they basically scan the whole of the northern hemisphere and then the whole of the southern hemisphere. And we get close to the ecliptic equator, something like a continuous period of 27 days. up to the ecliptic poles, where TESS actually gets you a full year's coverage in the JWST continuous viewing zone. So it's really geared towards finding targets.
When's it launching?
So that one will launch in 2017.
2017, right before the JWST goes up. So and that's an entire sky survey of transiting exoplanets. So that's going to be exciting. But it will not image directly. That's one of the things. Even though we said it's the future of exoplanet observations, that's not necessarily something that TESS will be able to do.
There's an image right there of TESS and the 4 cameras going on too.
Ah, okay. There's an image of the spacecraft, so that's cool. At last.
At last.
At last.
Okay, at last. So the ultimate goal, I think, of a lot of people working in the field of exoplanets right now is to find Earth 2.0, an Earth-like planet orbiting a solar-like star. And what they would like to be able to do is take images or conduct a survey and take images of these planets and then follow up by doing spectroscopy of the ones that are interesting to look for biomarkers, the usual things that we would look for as evidence that there might be the possibility of life on that planet. And to do that, you need to have a very large telescope. So there are 2 approaches. One is to build a 10, 12-meter telescope with a coronagraph, and another is to build a large telescope and use this external occulter that you mentioned.
Okay.
So in both cases, they're very challenging problems because you're trying to measure planets that are extremely close to their bright central star and are 10 billion times fainter. So you've got to knock down 10 billion times the light of the star so that you can bring up the contrast in the surrounding region enough to be able to identify the planets.
What's the acronym stand for? I always forget. What does that last stand for? Do you know?
Advanced Technology Large Aperture Space Telescope.
Oh, okay. And that was not one of the ones that used the NRO chassis, is it? Or am I?
No. So the ones that use those chassis is AFTA, which is also being called WFIRST.
WFIRST.
And that's the next mission that will come after JWST, and is another step where they will include a coronagraph that will allow them to take images of gas giant planets and possibly some super Earths.
Right. Okay.
So at last is kind of the end of the road, if you like, in studying Earth 2.0, and there are a number of steps along the way. JWST, then this mission called WFIRST, and then this big flagship later on.
Good. So there are a lot of. I just can't believe how many things are on the pipeline right now, being built and ready to be launched. One of them I'm most excited about is this thing that uses talk about occulting stars so that we can see the planets directly. Uses this thing called a star shade, and Scott has some pretty cool animations. Can you put one of those up for us?
I can. So I'm gonna load the first one first, just to show it unfurling. Because it's fantastic.
Yeah, so Mark, while he's doing that, why don't you describe what this is?
So the occulter is one of the concepts that people are looking at for doing this Earth 2.0 measurement. And the basic idea is that you can either make the large telescope with the internal coronagraph to extremely demanding specifications in terms of its stability. We're talking about tens of picometers here, and holding a big structure 10, 12 meters wide to that kind of tolerance. An alternate approach is to go with this external occulter, which is basically a mask that you fly something like 100 to 150,000 kilometers from the telescope, and you align the two so that this free-flying mask or occulter blocks out the light from the star and allows you to image the planets around the star with the coronagraph. And the nice thing about this approach is that it doesn't put any demanding requirements on the telescope. Instead, the demanding requirements are the mask, which is extremely big. We're talking 20 to 30 meters wide, and you have to fly it in formation with the telescope to keep them aligned. And then when you're ready to go to your next target, you have to fly it around the sky to align with your next target.
That's crazy looking at that.
It's swings and roundabouts.
I thought deploying JWST was intricate. Look at that thing.
Yeah.
I mean, that's amazing. And you said it was how big again? I'm sorry. You said 30?
Depending on the size of the telescope, they can be 20 to 30 meters diameter.
Okay, so this is a big thing we were talking about up in space. So
it is. Yeah.
And this is showing, this animation is showing how it blocks the light from the stars, and you can see these planets becoming visible once that's been done, because they are all that extraneous light is being blocked out. What's up with that shape? How come it's shaped that way?
So the shape is basically designed again to optimize or minimize the diffracted light from the edge of the mask itself. If you just use a circular aperture, that circular edge, creates a lot of scattered light or diffracted light that you don't want right where the planets will be. But by using this fully optimized shape, you can basically decide where you want the diffracted light to finish up. So it puts the scattered light where it's not going to interfere with your imaging of the planets. I think it's a simple way of sort of putting it.
So how is this thing going to be pointed? I mean, you've got this thing floating out in space. I mean, how do you point this thing?
Very carefully.
Right. So this is one of the challenges that people are working on right now. As I said, these things are still in what we would call the trade stage. So we're trading off the benefits of the occulter versus the benefits of the internal coronagraph, and they each have their pros and cons. And the idea is to figure out which one wins out at the end of the day.
Okay.
So, to align these things, you have to have a way of the telescope knowing exactly where the occulter is and being able to stay aligned with respect to the occulter.
Okay, so you just pointed out, this is still being in the design stage or early discussion.
Oh,
yes. So no timelines or anything like that for when this might get deployed.
Not yet. This is we're still in the sort of early days phase, I would say.
Okay, but that's something definitely that's gonna. And well, we know where it'll go, right? Roughly, will it go out to L2? Will it be something?
Right. Most of these missions now are looking at going to L2. In fact, they actually orbit L2. They're not at L2.
Okay, and let's talk real quick what L2 is.
Let's talk about it.
Yeah, I was gonna. Okay, I'll go for it, Scott.
So we're talking about Lagrangian points, which are a balance as far as where the gravity and the mass are within systems. So this is a particular point, and that's where JWST is going, and where we've had other things go as well. And so we have different points between us and the moon and the sun, and the way things are balanced out within the gravity field. We can hold them there with very minimal adjustments, and that's why with JWST, for instance, we do need to have some fuel on board to adjust, but it's going to be staying there primarily fairly easily and just at those balancing points between objects.
Right. It's a spot where it will match Earth's orbit as it goes around the sun, and it'll always be, we'll be able to look in the same region to be able to communicate with it and things like that. So it's a really important area in the solar system. It's also going to get really crowded there. Any worries about that, Mark? I mean, we're launching all this stuff and putting it at L2. Is there any worries about crowding it?
Not at L2. I mean, that's an extremely large volume of space. I mean, as you know, there's certainly growing worries about the number of satellites in low Earth orbit and the impact that debris when you launch and when you operate these satellites might have on the standard operational modes of the low Earth orbit ones. But out at L2, it's just not an issue because it's such a big volume.
So I guess exoplanets are probably one of the most exciting areas of astronomy right now. It's certainly one of the biggest growing, and we've got a lot not only in the building stages coming up and how we plan to observe exoplanets directly, and we've given you a brief overview of how some of those different ways and plans of the future. But I want to get to a couple of comments here. First of all, Craig Landon on YouTube is saying, why doesn't anyone mention TESS? I think we just did.
Yeah. There you go, Craig.
Yeah, there you go, Craig. So we talked about TESS. It's coming up 2017, like Mark said. It's going to be a really great piece of the exoplanet research puzzle. And here's one from. Let me see here. Oops, I just lost it. There it is. Mihailo Janovic from YouTube is also going, what do we need to do to get images of exoplanets similar to those of Ceres or Pluto by Hubble? Do we need to get 50-meter space-based mirror, or do we need much better camera technology, or even both? So
space unicorns.
Space unicorns. So what do we? I guess. So what do we need to be able to see smaller exoplanets like Pluto and Ceres?
In order to do that, you just need an extremely large aperture, because that's the only way you can actually resolve them. I mean, the better cameras might get you better contrast, but you'll never have enough spatial resolution to really be able to get the kind of resolution that this question is asking for. Right.
So a resolution, whether you can resolve something as a function of two things: the wavelength you're looking at and the diameter of the collecting surface. And so once you have, depending on what wavelength you're trying to look at it at, you can actually hope to resolve it. But these things are so small that to look at them in other systems would need an enormous telescope, one that I think is not even in the planning stages right now. So there's one here. There's a comment here that I want to just bring up on the Q&A app that has to do with the extremely large telescope. This is from Miko Ser, I think is how you pronounce it. With the new 40-meter European extremely large telescope, which is a tremendously imaginative name, he says, will it be able to directly observe extrasolar planets, or do you need a space telescope with a star shade? So the extremely large telescope, as opposed to the ESO has a very large telescope. Will it be able to see anything?
So they will be able to do direct imaging of gas giant planets very easily, I think, with that kind of aperture, and they'll be using additional techniques that we didn't really mention today, such as adaptive optics, which allow you to correct for some of the aberrations that you get in your optics from the atmosphere. So yes, they'll be able to do something. I'm not sure they will be able to directly image Earth-sized planets, maybe super Earths in special cases.
Right, and so here's something from Adam Synergy, also on the Q&A app. He's asking, what is the scientific value of direct imaging of exoplanets beyond producing a pretty picture?
So by getting direct images, you can do a number of things. You can get the orbit, which is always very useful, and there are other things that we also didn't really get into, such as doing time monitoring. You can time monitor these images and maybe see evidence of continents or different structures on the surface of the planet. And this kind of work has been...
Whoa! Now back up. You're telling me that we'll be able to see? We might be able to see continents?
Well, you can't see them, but you can see variations in the amount of light coming from the planet.
Oh, okay. It's kind of like that map of Pluto that...
yes, I was just going to say that. It's like that, and actually there have been some people who are trying to do, in a very, very coarse way, try to understand variations of the atmospheres of Jupiter-sized planets using Hubble. But if you have these larger telescopes that are much more capable in the infrared, extended infrared, you might be able to do that. So yeah, you're not going to see the little continents whirling around, but changes is what is. But it's very similar to the old Pluto observation. Same idea.
Okay, so the idea, the reflectivity of a planet might change, might be slightly darker, slightly brighter in some spots, depending on the topographic features it has.
Exactly, and there was actually a very nice demonstration of this by the Epoxy mission, which looked back at Earth when they were on their way to their last target, and they actually do see some of this structure in the time monitoring that they were able to do.
Yeah, who says we don't have creative names or imaginative names? Epoxy.
Yeah.
We spend a lot of time thinking up those names when we write.
Absolutely, yeah, over beer. I was just going to mention, we were talking about very large telescopes. As you've seen in the animations, James Webb Telescope does not have a solid mirror. And so when you're talking about imagining and having discussion over beer about how large those telescopes would have to be to image, a very minor planet, those part of the idea that many people think that if we ever do this, they'll have to be in segments. There's no way that a monolithic mirror is going to be sent up there. It's going to be in pieces. And James Webb is a pathfinder for that, because we have these great segments that are going to be aligned and work fantastically.
Okay, so Carol, I think I have one for you here. It's from Michael Job, and he goes, when I first read this question, it was like I was thinking of the Greek sandwich. So how are the gyros doing? I guess presumably on on HST. How are the gyroscopes?
They're doing okay. We had a problem with one which is not working. There's a second one which was monitored. We have like 6, and the second one did not fail, but I think they're resting it. And so, and in addition, so we have plenty of gyros left because we have redundancy in the system. And the other thing is there have been studies done of what if you only have 3, what if you only have 2, that kind of thing. Can we still do science? But because of the redundancy of the gyros, we're doing great. HST's doing just great.
Yeah, and I think that it probably would have done better science if we had launched it with gyros instead, but, you know.
At least with some tzatziki sauce on it.
Yeah, right. For lubricant, yeah, exactly.
So I got that image from you, Carol. I finally got that image.
So there was a question of why does Mark call James Webb Telescope JW, and it's because he's very close friends with it. And Mark will kill me for this, but whatever. Actually, this is a great picture, haha, but actually it was pretty awesome that where you can see a person standing, so that gives you the idea of the size. And this was during some testing when Mark got to stand right there and be imaged all over the place.
Right. It just shows that we really are involved in every aspect of the production of the telescope.
Okay, you can get rid of that image now because
I'll put it up on Twitter.
No, damn it.
Yeah.
Between Mark and my friendship. Okay, that's it.
Okay, so let's see. Let me see if I can find a couple more here. Okay, so this was from Michael Luthhauser from the Q&A app. Are there any other solar systems similar to us in the Milky Way? If so, where are they? Now, I think this would be the context of this is, you know, maybe what Kepler has found, something like that. So, what do you say, Mark? Any other solar systems similar to ours?
If you're talking about an exact copy, I think not, but Kepler's finding solar systems with lots of planets. There are several that have almost as many as our solar system. We're starting to find Earth-sized planets in the same region as Earth, what we call the habitable zone. So as we find more and more of these systems, they're starting to look more and more like our solar system in some ways and different in others. So as I said, a lot of these systems have a different distribution of planet sizes to our own solar system. So I think what we're really seeing is that there's a very large diversity of different kinds of systems as we look around with Kepler.
Okay. Here's a good one also from the Q&A app from Eamon Fanton, who asks, they declare planets of a specific mass at a specific distance from a star. How can they be so sure? They know the planet is there by the star wobbling, but they have no idea of the total mass of all planets orbiting. How can it be so? How can they be so precise? And so there's kind of an embedded thing in there. When you see a star wobbling because of a planet in orbit around it, how can you be so sure it's just that due to that one planet, not a whole bunch of others that we don't necessarily see? How can you be so precise?
Well, the answer to take the last part of that question, the longer you look, the more likely you are to find evidence of additional planets in these systems. So, you know, back in the late 90s, people were announcing individual planets. As time has gone by, these radial velocity surveys have started to add additional planets to those systems. In answer to the question about precision, well, that comes from adding the transits in as well. As I said, once you've got the transits for these systems and the radial velocity measurements, you've got the mass, you've got the orbit, you can be extremely precise about what you're seeing because you've got data that prove the numbers.
Yeah. So, and the specific distance, does that come from the speed with which the planet goes across the surface or transits, or is that how you get that information?
Well, yeah, I mean, it can come from the transits. If you have a transit every 4 days, then you can figure out what the orbit is, especially once you know the size of the planet as well.
Okay. All right.
As I tell my friends, it's just physics.
It's only physics.
It's only physics.
It's only physics. He also asked, same guy, Michael, asks, where's Hubble data? The mass archive. You want to answer that, Carol?
Sure. So there's lots of imagery that's available through HubbleSite.org. So if you go to HubbleSite, S-I-T-E, HubbleSite.org, there's lots of images and explanations of the images and the press releases. And then the actual science data from Hubble. We will also have the James Webb Telescope data when it comes down. We have the Kepler data. We will have the TESS data. And we have 10 other satellites which have data in our archive, and it's archive at STSCI, that's our institution, Space Telescope Science Institute.edu. Archive.stsci.edu, but you can say Space Telescope Archive on Google and you can find it. And there is an interface into that data. You can get GIFs of some of the data. Now, it's science data, and it needs to be processed carefully so that all the instrument signature is taken care of, the cosmic rays are removed, but that data is all there, and it's made public in a timely fashion after the observations have been taken.
Yeah, we have done hangouts in the past on how to get Hubble data and done some preliminary processing on it with Zolt LeVay. Scott and I were talking today about maybe doing another one.
You're right.
So look for more hangouts on how to get Hubble data in the future. And
I think you did one on the Hubble Legacy Archive as well.
That's true.
That was touched up. So there are 2 hangouts already in the archive where we have in the Hangout archive where we have discussed how you get the data.
Right. So Scott, am I missing anything? I'm looking. You guys don't tweet. You just it's like Scott Lewis is owning Hubble Hangout hashtag here.
I own Twitter. Sorry, everybody.
Yeah. What?
It's because you can't tweet as Hubble while you're hosting the show. So
I know.
We need to figure that out.
Yeah. I guess we can work out some technical. I can't do too many things at once, or else my head explodes.
But maybe
have I missed anything?
Yeah. I do have some here. So and it's more of exoplanets in general. So one from Alessio Mangoni. It was in relation to the radial velocity image I put up there. And like, could the star's orbit really be affected by the exoplanet's gravity? I mean, if the spectre's fingerprint changes in time, wouldn't it be too subtle if related to the exoplanet's pull on the star? So, I mean, first of all, with that, we know that they both have mass, and so there will be a center of mass between them. It's not as if one takes all the mass and the other one's massless. So they have to have a center of mass between them, and that's the biggest point of why we're able to see them shift.
And if you could detect the spectra, both spectra, on top of each other, one of the star and the other of the planet, if it was bright enough, then you could see the shift in both objects, and in fact we do in binary stars that are similar in brightness. Yes, you would see the shifting because the objects orbit each other, and so that spectroscopic shift would manifest itself in the planet and the star too, but we just can't, the planet's too faint, so we can't do that.
Petaflux, I just want to mention his comment. He goes, I want an Earth-sized mirror in orbit. Yeah, wouldn't that be great?
Okay. Well, a moon-sized mirror, we've talked about that, but...
Yeah. Well, after we get our Dyson sphere set up, we'll be good with the...
Yeah, right. Yeah,
that'll
be 2019 after that.
Okay. So, I have another one, too, and it's more about exoplanets in general. So this one's from Eamon Fenton on Google Plus in the event page. And we're told that we found exoplanets of a certain mass and at certain distance from their parent star, but how can we be so sure? What gives us that information we know their distance?
Again, it comes down to, for instance, the transit data. You see the dip in the light coming from the star as on a very regular basis, and you can calculate the size of the body that's causing that dip. So it's just physics, as Carol said. It's very simple physics too.
And you can
Right. So we're just studying the orbits. So we're able to know the mass and everything like that. So
yeah.
Right. Okay. Well, Mark, this has been awesome. Thank you so much for joining us.
Fantastic.
You're going to come back, right? You're going to talk about JWST and the deployment of the sunscreen or the screen.
I'd be happy to do that, and I've also, just by way of advertising, tell people that if they go to the jwst.gsfc.nasa.gov website over the next 2 months, they'll be able to watch mirrors being mounted into the backplane of the telescope.
That's right. There's a camera in the clean room. There's a live camera.
I'll be sharing out those links later through Google Plus. Facebook, everywhere.
It's really cool that you can see the whole thing going on, and that is pretty much live, isn't it? Or is there a delay? And when those,
I'm sorry?
Those are pretty much live images, right? Or is there a delay?
They are live images.
Okay.
They're on a time. They take an image every few seconds. So
that is just amazing.
Okay, so keep an eye out for that hangout, and you may be asking, how do I know where these hangouts are? It's all on hubblesite.org/explore or get involved/Hubble Hangouts. That's where I'm putting all of the schedule. You can also follow us on Twitter at Hubble Telescope. You can also add us on Circles on the Google G+ page. We also post on our Facebook page as well, and that's where all of the hangouts will be announced. Next week, Carol Scott and I will be talking with Niku Madhu. His name is longer than that, but I was told to just go ahead and cut it short. Who has been using Hubble to look at some exoplanets, Jupiter-sized exoplanets. He's found they were looking at 3 of them, and they were looking at the water vapor on those exoplanets and found them to be surprisingly dry. So that was a press release that came out last week. And we will be talking with the principal investigators who made that observation. So more on exoplanets next week. That's Thursday at 3 o'clock Eastern Time, 7 o'clock Universal Time. So
and noon Pacific for me in LA. Because
sorry, Scott. Way out.
Can't forget about me.
No.
So Carol, thank you. It's been a lot of fun as always. And Scott, thank you. Excellent driving. We didn't crash once, so good job.
Not once.
All right. All right, folks. So thank you all for watching. And
thanks very much, Mark.
Yeah,
thank you. You were awesome.
Fun. Thanks.
All right, thanks.
Thank you all for watching, and as always, keep looking up.
Exceeded, and when they have problems, I'm the guy that gets to sit down with them and help them figure out how they can meet our requirements and still, meet the budget or the schedule.
Oh, so really not very much then. You don't really have much to do with.
Yeah, he's never busy.
No, they keep me very busy. So
you sound like an underachiever there.
Yeah, really. Is that all you're doing?
Is that all? Yeah, really.
Yeah.
Jeez.
Okay, well that sounds great. Well, I hope to get some more insights into the status of JWST a little bit later on in the Hangout. But before we do that, I want to talk a little bit about your research interests. Before you were building the James Webb or coordinating all these efforts, what's your primary research interest?
So my primary research interest has always been direct imaging or taking pictures of debris disks, which are the early stages of the formation of planets, and then actually trying to directly image planets themselves. So I started off 20 years ago building an instrument called a coronagraph, and I guess we'll get into how coronagraphs work later on, for telescopes that would be put on the Chilean telescopes down in at La Silla and then La Serena. And then I slowly evolved to working on flight hardware, and I actually helped build the advanced camera for surveys, which had a coronagraph.
That's on Hubble.
That's on Hubble. So I've always kind of worked on building hardware to do this kind of problem, and we started off, as I said, studying debris disks, and the more you get into imaging debris disks, the more you want to sort of go the next step and actually be able to directly image the planets. So that's what I've been kind of working on with Hubble on and off for the last 10, 15 years.
Right. So today's hangout topic obviously is about exoplanets, but one of the things that really amazes me about this branch of astronomy or research is that this really is a pretty brand new research area, isn't it? You said yourself 20 years ago. That pretty much marks the beginning of exoplanet research, doesn't it? I mean, we haven't been doing this for very long.
No, that's correct. It's about 20 years, and
There we go.
Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we've got a really interesting hangout planned for you today. We have Dr. Mark Clampin from the Goddard Space Flight Center here to talk to us about exoplanet observations, both past, present, and the future. And so we're looking. This should be a very interesting hangout. So we hope you will bring lots of questions and comments. Which brings me to how you can interact with us. We hope you will send us questions with the Q&A app on YouTube and the Google Plus event page. We're also monitoring the Hubble Hangout hashtag on Twitter, and you can also comment on the Google Plus event page itself. So we're monitoring all these different avenues for you to interact. So we hope to get lots of great questions from you later in the Hangout. With me also is Dr. Carol Christian. She is from the Space Telescope Science Institute as well. Hi, Carol.
Hello.
And Scott Lewis.
How's it going, Tony?
Hey, you ready to drive the internet?
I'm always ready to drive the internet.
I know, you're an expert driver, NASCAR of the internet drivers.
F1, no NASCAR. I know how to maneuver.
Picky.
So as I mentioned, our guest today is Dr. Mark Clampin. He is the Observatory Project Scientist for the James Webb Space Telescope at Goddard. Welcome, Mark.
Hi. Thanks for having me.
I'm really excited to get you on in a hangout because you've got a lot of great research going on. You're involved in all kinds of great things. But first, I have to ask you, Observatory Project Scientist. How is that different? What does that mean? And how does that differ from, say, just a regular project scientist?
Well, it comes down to the fact that James Webb Space Telescope is such a massive project, and it's a very large telescope. So my job is to be responsible for the observatory, which is three pieces: the telescope, the sun shield, and then the spacecraft bus. So my job is to work with the engineers to make sure that the science requirements for the telescope for the observatory are met, or preferably planets where you're looking for a few % dip. As you start trying to look for terrestrial planets, then it becomes a real problem because you need to have extremely precise photometry. And that's why we've had to go into space to really look for the Earth-size planets. And that's, as you know, that's what the Kepler mission has been doing for the last 6 or 7 years. It's just been staring at 150,000 stars, trying to find the ones that have transits that are directly traceable to something the size of a sort of small rocky planet. So it gets very easy to very, very hard.
Here's an example for Kepler too. And you'll be able to see, I'll have it pop up here in a second, where we're seeing those dips in brightness that's being detected on the lower right-hand side of the screen, right here.
Right.
So that big dip.
That's a very generous light curve.
Right.
Yeah, really beautiful.
Yeah.
No noise.
Right, and when you look at real data, without doing the analysis of the data and the processing, it's very hard, especially for the small planets, to see any dip at all. You need a pretty big planet to give you a... So this technique really thrives on, especially when you're trying to do the small planets, on having as much light as possible, even from very bright stars. So this is one of the reasons why JWST is going to be such a powerful tool for doing this kind of science.
Yes, we'll get into that in a little more detail in a bit. But
we have used HST to do this. I mean, people did want to try and just get a feel for an HST-sized telescope, what could be done. It's not a primary thing that we do because these other observatories will concentrate on that, but a few observations were taken with HST just to make sure we knew what we were up against.
Right.
Yeah, and I think, Carol, and correct me if I'm wrong, but the reason HST isn't ideally suited for this kind of work is that generally these light curves take many days to, sometimes, depending on the period of the planet, to create, right? So you really kind of need to take up a lot of Hubble time to get a decent curve, right?
Right, and that's why, as Mark says, the strategy that...
And bring that up. So,
Yeah.
Scott, I believe you've got a good illustration of what the transit method is. So let's talk about, before we get to the future of exoplanet observations, let's talk about how it's been done in the past. As we've talked about, exoplanet research is a new field, very young, very exciting, red hot right now in astronomy, yeah. And the observations have been done primarily by looking at very, very tiny dips in brightness of a star. And Scott has this up now. Basically, when a planet passes in front of a star, it gets just a little tiny bit dimmer, and as the light is blocked from the star. And Dave, I'm sorry, Mark, I'll let you go ahead and explain this animation a little bit.
Okay, so the animation is just showing what happens when you look at a star where the planet is actually moving across the face of the star as it orbits that star. And so what happens is you see a very tiny dip in the amount of light coming from the star as the planet orbits across the face of the star. And the dip is basically a function of the area of the star that you're looking at and the area of the planet. So large gas giant planets like Jupiter's might produce a dip of a few percent, whereas if you were looking at a terrestrial Earth-like planet, then the dip is much smaller. It's about 0.05%, and then it becomes a very challenging measurement. But just looking at some of these big Jupiter planets, that's the kind of stuff you can do with a very simple telescope, as we were talking about a few minutes ago.
Right, and this was among the first measurements we made, or the first ways in which we detected exoplanets. And this is an indirect method, meaning that we're not seeing the planet directly. We're seeing the effect of that planet in orbit around the star, and inferring the existence of that planet being there. How hard is this to make? How hard is this to make? I mean, we said we can do it with amateur-grade instruments, but we can do better jobs with bigger telescopes. Correct? I mean, how hard is this measurement?
It's not too hard, as I said, if you're trying to just do gas giant. It's just a rapidly expanding field. A lot of the new young people coming into astronomy are all sort of coming into this field because there's just so much going on. There's new planets being discovered every day. It's just a really exciting and dynamic field right now. And
correct me if I'm wrong, but this field, exoplanet research, really had, I think, pretty humble beginnings, from my understanding. I mean, I remember at the High Altitude Observatory, there was people there observing a project called STARE, S-T-A-R-E, which basically used Meade telescopes in a parking lot to, and this was with Dr. Charbonneau and was it Mike Brown? It was, oh gosh, I'm dating myself now. But anyway, they were looking at exoplanets, or trying to find exoplanets, presumably with the transit method, which we'll get to in a minute, with amateur-grade instruments.
Exactly. I mean, well, as you said, we'll talk about transiting exoplanets in a minute, but I think one of the amazing things about studying transits is you can actually stand in a car park like Dave Charbonneau did with a celestron telescope and take data that shows you there's an exoplanet orbiting a star. That's pretty amazing.
Yeah, gosh, it was about a year and a half ago, I held a hangout on here where I had one of our amateur astronomers that works with the AVSO, and we did a live observation of a transiting exoplanet. So we're able to get the data there and show the curve going on afterwards and talk about what was going on. These are things that can be done by everyone, and it's amazing. And this is how we are using advanced telescopes, out orbiting in space, and also very large telescopes here on Earth to discover completely new worlds.
Exactly. The transiting exoplanet method is great because it just scales from your telescope in the car park all the way up to James Webb Space Telescope, and at every step or every scale you can make lots of really amazing new discoveries.
All right. Well, let's go ahead and